Hi. In this lecture, we're going to focus on the major topographic features of the ocean floor and how they're organized across an ocean basin. Rather than examining the ocean as a flat surface, we will look beneath the water to understand how the seafloor changes from the edges of continents to the deepest parts of the ocean. Our goal is to understand what these features are, how they form, and why they occur where they do. We will move systematically from continental margins into the deep ocean basin, examining features such as continental shelves and slopes, abyssal plains, mid-ocean ridges, seamounts, and deep-sea trenches. By the end of this lecture, you should be able to describe the basic structure of an ocean basin, recognize the major seafloor features, and using knowledge from previous lectures, be able to explain how large-scale Earth processes shape the topography of the ocean floor. Ocean topography matters because the shape of the seafloor directly affects how the ocean functions. The height and depth of the seafloor influence the movement of deep ocean currents by steering or blocking water flow. These currents in turn play a role in distributing heat, nutrients, and oxygen throughout the global ocean. Topography also influences marine ecosystems. Different depths and slopes create a distinct habitat, from shallow continental shelves to deep abyssal plains and trenches. Finally, ocean topography records the long-term processes that shape Earth's surface. The seafloor preserves evidence of crust formation, sediment accumulation, and deformation over millions of years. In this sense, the ocean floor is a geological archive. A helpful way to understand ocean topography is to imagine a cross-section across an entire ocean basin. Starting on land, moving offshore, crossing the deep ocean, and ending at the far edge of the basin. Along the transect, we encounter a predictable sequence of features. This sequence is not accidental. It reflects systematic changes in crust type, crust thickness, sediment accumulation, and long-term Earth processes. As we move across the basin, we will examine each feature in order and discuss why it exists and how it fits into the overall shape of the ocean floor. The continental margin is the submerged outer edge of a continent and represents the transition between continental crust and the deep ocean basin. When we talk about the continental margin, it's important to be very clear about what defines a continent from a geological perspective. One of the most common misconceptions is the idea that continents end at the coastline. In reality, the coastline is a visual and political boundary. It's not a geological one. Geologically, continents often extend far offshore beneath the ocean. The continental margin represents the submerged outer edge of a continent, and it includes the continental shelf, the continental slope, as well as the continental rise. Together, these features form a gradual transition from shallow coastal waters to the deep ocean floor. Understanding the continental margin is essential because it links terrestrial and marine systems and plays a major role in sediment transport and biological productivity. Even though these features are underwater, they are typically underlain by continental crust, not oceanic crust. The distinction between what is continental crust and oceanic crust is not based on whether the crust is underwater, but more so based on its composition, thickness, and density. Remember, continental crust is generally thicker, less dense, and composed of different rock types than the oceanic crust, which is often heavier and thinner. Because it is less dense, continental crust can remain elevated even when submerged beneath seawater. The transition from continental crust to oceanic crust usually occurs beyond the continental margin, near the base of the continental rise, beneath the deep ocean basin. At this point, thick continental crust gives way to thinner, denser oceanic crust, and the seafloor drops to much greater depths. Understanding this transition helps explain why ocean basins have a step-like structure and why large areas of continental crust can exist underwater. The continental margin is therefore not just a shoreline feature, but a fundamental structural component of the ocean floor. The continental shelf is the shallow, gently sloping region that extends outward from the coastline. Although shelves can extend hundreds of kilometers offshore, they are typically less than a few hundred meters deep. Importantly, the continental shelf is composed of continental crust and is therefore part of the continent, not the deep ocean basin. As a result, large areas of the continental crust form broad, shallow platforms rather than steep slopes or deep basins. Continental shelves are generally shallow, extending from the coastline to depths of roughly 200 meters. Because of its shallow depth, sunlight can penetrate to the sea floor across much of the continental shelf. This allows photosynthesis to occur, making shelves among the most biologically productive regions of the ocean. Many major fisheries are located on continental shelves, and these regions have strongly influenced by changes in sea level over Earth's history. The continental slope is the steeply inclined region that connects the shallow continental shelf to the deeper parts of the ocean basin. Unlike the shelf, which slopes very gently, the continental slope marks a rapid increase in water depth over a relatively short horizontal distance. The continental slope begins near the shelf break at around 200 meters depth and descends steeply to depths of several thousand meters. Importantly, the continental slope does not mark the immediate transition from continental crust to oceanic crust. Instead, it represents the structural edge of the continent, where continental crust begins to thin and taper outward. Although the slope is still underlain by continental crust, that crust is becoming progressively thinner and more stretched in this region. The steepness of the continental slope reflects this change in crustal structure rather than erosion alone. As continental crust thins toward its outer edge, it can no longer support a broad, shallow platform like the continental shelf. The result is a sharp drop-off toward deeper water. Beyond the continental slope, sediments transported downslope accumulate to form the continental rise. and the true transition to oceanic crust typically occurs farther offshore beneath the deep ocean basin. Understanding the continental slope as a zone of crustal thinning rather than a sharp crustal boundary helps explain why continental margins have a step-like shape and why large portions of the continental crust can exist underwater. Submarine canyons are deep, steep-sided valleys that cut into the continental slope. Although they resemble river canyons on land, they form through very different processes. The primary mechanism responsible for carving and maintaining submarine canyons is sediment transport by gravity-driven flows, especially turbidity currents. A turbidity current occurs when sediment on the continental shelf or slope becomes unstable and begins to flow downslope under the force of gravity. These flows are made up of a mixture of water and suspended sediment. Because the sediment makes the mixture denser than the surrounding seawater, the flow accelerates as it moves downhill along the seafloor. A turbidity current is best thought of as an underwater avalanche, but instead of solid snow sliding through the air, it is a dense mixture of sediment and water flowing through less dense seawater. You can visualize a turbidity current on the left image on the screen there. As a turbidity current travels downslope, it can transport enormous amounts of sediment from shallow regions in the deep ocean. The sediment within the flow is gradually sorted by size as the current slows. Larger, heavier particles settle out first, closer to the slope, while the finer particles remain suspended longer and are carried farther into the deep ocean. Over time, repeated turbidity currents carve submarine canyons and deliver sediment to deeper parts of the ocean basin, including the continental rise and abyssal plain. These processes provide an important connection between continental margins and the deep sea floor. At the base of the continental slope lies the continental rise, a broad, gently sloping region formed by the accumulation of sediment delivered from the slope above. Over millions of years, sediments carried by submarine canyons and gravity flows build up thick deposits at the base of the slope. The continental rise marks the transition from the steep continental margin to the relatively flat deep ocean floor. Its presence reflects long-term sediment redistribution rather than any sort of tectonic activity. The abyssal plains are vast, flat regions of the deep ocean floor, typically located several kilometers below sea level. By the time we reach the abyssal plains, we are firmly within the deep ocean basin, and the seafloor here is underlain by oceanic crust, not continental crust. Remember, as I said earlier, this transition from continental to oceanic crust does not occur at the shoreline and is not marked by a sharp surface boundary. Instead, continental crust thins progressively across the continental margin, and the true transition to oceanic crust occurs beneath the deep ocean basin, beyond the continental rise. Despite their great depth, abyssal plains are among the flattest places on Earth. Their flatness results from the slow accumulation of fine green sediments that blanket and smooth the underlying volcanic topography of the ocean crust. Over millions of years, The sedimentation buries seafloor irregularities, producing remarkably uniform surfaces. Abyssal plains therefore represent stable, low-energy environments in the deep ocean. Their shape reflects both the nature of oceanic crust and the long-term processes of sediment transport and deposition that operate across entire ocean basins. In the context of oceanography, convergence involving oceanic lithosphere is especially important because it leads to subduction, which is the primary mechanism by which oceanic crust is recycled back into the mantle. By this point in the course, we've already discussed mid-ocean ridges in the context of diverging plates and seafloor formation. Here, I want to take a step back and think about the mid-ocean ridge system as a global topographic feature rather than a single location. The mid-ocean ridge is not a short, isolated feature. As you can see on the map here, it is a continuous volcanic mountain chain that extends through all of the world's major ocean basins, making it the longest mountain system on Earth. Although it is broken into segments by transform faults, it functions as a connected global structure. Look at the map on this slide and follow the ridge from the center of the North Atlantic Ocean southward and through the Southern Ocean, where it then connects to the Indian Ocean and eventually to the Pacific Ocean. Topographically, the mid-ocean ridge is elevated relative to the surrounding abyssal plains because the oceanic lithosphere there is hot and buoyant. However, it is important not to misinterpret this elevation. Even though the ridge is higher than the surrounding sea floor, it is still part of the deep ocean. Typical water depths at the ocean ridges are on the order of 2,000 to 3,000 meters, compared to abyssal plains that are often 4,000 to 6,000 meters deep. So while the ridge represents a topographic high on the ocean floor, it is not shallow in the way continental shelves are. In other words, the mid-ocean ridge is a mountain chain that exists entirely within the deep ocean basin. Its elevation reflects thermal and structural differences in the oceanic crust, not proximity to the sea surface. Seamounts are isolated underwater volcanic mountains that rise from the seafloor but do not reach the ocean surface. They form from localized volcanic activity associated with the hotspots we spoke about in a previous lecture. Therefore, they often occur far from plate boundaries. Some seamounts have flat tops and are known as geodes, indicating that they once extended above sea level, where wave erosion flattened their summits before the seafloor subsided. In addition to recording volcanic activity and long-term cooling of the lithosphere, seamounts and geodes play an important role in ocean dynamics. Because they rise thousands of meters above the surrounding abyssal plains, they disrupt the flow of ocean water moving across the sea floor. When deep ocean currents encounters a seamount, the flow is forced upward and around the feature. This interaction can enhance vertical mixing, bringing colder, nutrient-rich deep water toward the shallow depths. As a result, seamounts often support elevated biological productivity compared to the surrounding deep ocean. Over long time scales, this interaction between topography and circulation contributes to how heat, nutrients, and chemical properties are distributed throughout the deep ocean. So while seamounts and geodes may appear to be isolated geological features, they are important links between seafloor topography and the physical and biological behavior of the ocean above them. The deepest features on the ocean floor are deep sea trenches, which are long, narrow depressions that can reach depths greater than 10,000 meters. Trenches represent the most extreme topography on Earth's surface and stand in sharp contrast to the broad, flat abyssal plains we just discussed. Recall that deep sea trenches form as a result of subduction, typically when an old and heavy oceanic crust is being pushed under a continental plate. We spoke about that in a previous lecture. As an oceanic plate approaches a subduction zone, it cools, becomes denser, and begins to flex downward under its own weight. This bending creates a deep, narrow trough at the plate boundary, and that's the trench. The extreme depth and steep sides of trenches reflect the mechanical bending of a rigid plate rather than gradual surface processes. From an oceanographic perspective, trenches are important because they represent regions of profound depth, high pressure, and relative isolation. They influence local circulation patterns, affect how sediments are trapped or redirected, and create unique physical environments on the sea floor. These two illustrations here are meant to help put the depth of deep sea trenches into perspective. The deepest point in the Mariana Trench reaches approximately 10,994 meters below sea level, while the summit of Mount Everest rises about 8,848 meters above sea level. So if Mount Everest were placed inside the Mariana Trench, its peak would still be more than 2 kilometers below the ocean surface. That means you would have to travel 1 mile below the surface to reach the top of Everest. This comparison highlights just how extreme trench depths are and emphasizes that the deepest parts of the ocean far, far exceeds the height of Earth's tallest mountains. Also notice the depth of the trench is deeper than the standard cruising altitude of commercial airplanes. Only a few human beings have ever reached the bottom of the trench. Perhaps the most famous person is James Cameron, the movie director that gave us such films as The Abyss and Avatar. Can you believe his submersible captured video footage of a plastic bag, a plastic 5-gallon bucket, a balloon showing characters from the film Frozen, and even a candy bar wrapper at the bottom of the trench? Yes, even at that depth, humanity's negative impact on the planet is being realized. So when we step back and view the ocean basin as a whole, we see that its shape is composed of repeating sets of features: continental margins, abyssal plains, mid-ocean ridges, and trenches. Each of these features reflects a different process operating over long timescales. Together, they form a coherent and predictable pattern. Ocean topography is therefore not random. It reflects the interaction between Earth's interior, sediment transport, and the long-term geological processes. I challenge you to take some time now to carefully consider how the last few lectures are connected to reveal that Earth's underlying core composition provides the very specific requirements necessary for lithosphere plates to interact in ways that create not just unique topography and relief, but also to create new ocean floor. If you struggle to connect these lectures, then I encourage you to spend more time with your notes and visit me during office hours. Before we finish today, it's useful to introduce four broad terms that describe how we divide the ocean spatially. The first two terms are based on whether we are referring to the seafloor itself or the water above it. The benthic zone refers to the seafloor and everything associated with it, regardless of what the depth is. Whether we are talking about the continental shelf, the abyssal plain, or even a deep sea trench, all of those environments are part of the benthic zone. In contrast, the pelagic zone refers to the open water above the seafloor. This includes all of the water column, from the surface down to just above the bottom. Importantly, pelagic does not mean deep. It simply means not on the bottom. These terms allow us to distinguish between processes and organisms associated with the seafloor versus those associated with the open water above it. For example, a flounder or other species of flatfish that typically buries themselves into the seafloor would be considered a benthic organism, as would a horseshoe crab that crawls along the bottom. Whereas a shark or a dolphin or a tuna that swim through the water column, they would be considered pelagic. We can also divide the ocean based on its position relative to continents. The neritic zone refers to shallow ocean waters that lie above the continental shelf. Because these waters are shallow, they receive sunlight and are strongly influenced by land, making them some of the most productive regions of the ocean. The diagram on the slide shows a vertical line that represents the end of the continental shelf. The neritic zone is to the left of that line since it is all above the shelf. Beyond the continental shelf, to the right of the line, lies what we consider the oceanic zone. This includes the open ocean waters over the continental slope, rise, and abyssal plain. These waters are generally deeper, farther from land, and less directly influenced by terrestrial input. Please note these terms are not mutually exclusive. A benthic organism may be neritic or it could be oceanic. Likewise, a pelagic species could be neritic if it generally lives above the continental shelf, or it could be oceanic if it lies above the abyssal plain. In the next lecture, we will focus specifically on deep sea basins. We will examine how basin shape influences sediment accumulation, deep water circulation, and the long-term evolution of the ocean floor. Ocean topography provides the framework for understanding these processes. By understanding the shape of the seafloor, we are now prepared to explore how deep sea basins function as a dynamic component of the global ocean system.